China may have just found a way around the most powerful technological chokehold in modern history, and the global semiconductor industry is not ready for what comes next. For decades, one Dutch company's machines have been the sole reason the world's most advanced chips exist, and Western governments have used control over those machines as their most powerful weapon against China's tech ambitions. China produces over $300 billion worth of electronics annually. Yet it couldn't manufacture its most advanced chips without foreign permission. You heard that right. The world's largest electronics manufacturer couldn't build its own cutting-edge chips because it was locked out of a single category of machine made by a single company in the Netherlands. But China just developed a way to make that lock irrelevant. To understand why that is so alarming to the industry, you first need to understand exactly what that lock is and just how absolute it has been. The machine that controls the world's most powerful technology. There is a building in Veldhoven, Netherlands, where the most consequential manufacturing equipment on Earth is assembled. The machines built inside that building are so complex, so precisely engineered, and so difficult to replicate that only one company in the entire world knows how to make them. That company is ASML. And the machine it builds, the Extreme Ultraviolet Lithography System, known as EUV, is the reason that every cutting-edge chip inside your smartphone, your laptop, your car, and the AI systems reshaping the global economy actually exists. To understand why this matters, you need to understand what a chip actually is at the physical level. A modern processor contains billions of transistors, tiny switches that control electrical signals packed into a piece of silicon smaller than your thumbnail. To print those transistors onto silicon, manufacturers use a process called lithography, essentially projecting a pattern of light onto a photosensitive surface, the same fundamental principle as photography, but operating at a scale so incomprehensibly small, it defies intuition. The most advanced chips being manufactured today have features measured at 2 nanometers, roughly the width of 10 hydrogen atoms placed side by side. To print features that small, you need light with an extremely short wavelength. EUV light has a wavelength of 13.5 nanometers, so short that it is absorbed by virtually every material it contacts, including air. ASML's machines generate this light by firing powerful laser pulses at microscopic tin droplets 50,000 times per second, creating plasma that emits EUV radiation. That radiation is then focused and directed through a system of mirrors so precise that their surface imperfections are measured in fractions of an atom. The entire machine stands over 30 feet tall, weighs nearly 180 tons, contains over 100,000 individual components, and costs approximately $350 million per unit. But this is where the story stops being about engineering and starts being about power. Because ASML doesn't just make a difficult machine, it makes the only machine. There is no second supplier. There is no alternative technology currently capable of matching EUV's ability to print features at this scale in a production environment. Every company on Earth that manufactures advanced chips, TSMC, Samsung, Intel, depends entirely on ASML's continued willingness and ability to supply them. If ASML stopped shipping tomorrow, the global production of advanced semiconductors would halt within months. Then comes the part that transforms this from a business story into a geopolitical weapon. The United States government recognized this chokehold and moved decisively to exploit it. Working with Dutch and Japanese authorities, Washington effectively restricted ASML from shipping EUV machines to China, blocking Chinese chipmakers from accessing the one tool required to manufacture chips at the most advanced nodes. The export controls didn't just slow China down. They were designed to freeze China's semiconductor capability at a generational disadvantage, permanently locking Chinese manufacturers out of the sub-7 nanometer chip production that powers AI processors, advanced military systems, and next-generation computing. For years, it worked. Chinese chipmakers like SMIC were forced to manufacture at older, less efficient nodes using older lithography technology. The gap between what China could produce domestically and what TSMC was printing for Apple and Nvidia grew wider with every new chip generation. The Western assumption was that this gap was insurmountable. that without EUV, China was simply out of the race for advanced semiconductor manufacturing indefinitely. That assumption just became the most expensive miscalculation in the history of the technology industry. But to understand why China's breakthrough is so threatening, you first need to understand exactly how deep the wound of these export controls actually went. Why China has been locked out and why it matters. Imagine spending decades building the largest electronics manufacturing ecosystem on Earth, assembling more devices, exporting more technology products, and training more engineers than any other nation in history, and then discovering that the single most critical component of your entire industrial ambition is a machine you are legally forbidden from purchasing. That is the reality China has been living with. And the frustration, the urgency, and the national determination that reality created is precisely what drove the breakthrough the industry is now scrambling to respond to. When the United States began tightening semiconductor export controls against China, accelerating dramatically from 2019 onward, the restrictions didn't just block EUV machines. They blocked the chemicals, the software, the subcomponents, and the technical knowledge required to build advanced chips through any conventional pathway. The controls were designed with one explicit goal: to ensure that China could not manufacture chips below a certain feature size threshold, regardless of how much money, talent, or industrial capacity it threw at the problem. The logic was straightforward. Advanced chips are the foundation of artificial intelligence, hypersonic weapons guidance systems, electronic warfare capability, and next-generation computing infrastructure. Keep China from making them domestically, and you maintain a decisive technological and military advantage indefinitely. But this is where the strategic calculation carried a hidden flaw. The export controls assumed that the only path to advanced chip manufacturing ran through EUV lithography, through the specific technological approach that ASML had perfected and that Western governments could control. They assumed that China would be forced to either purchase access on Western terms or fall permanently behind. What they did not fully account for was the possibility that China would stop trying to walk through the door they were blocking and simply build a different door entirely. The pressure created by these restrictions didn't demoralize China's semiconductor industry. It focused it. Beijing poured hundreds of billions of dollars into domestic semiconductor research and development through its National Integrated Circuit Industry Investment Fund, known internally as the Big Fund. Universities redirected entire engineering departments towards semiconductor research. State-owned enterprises were given explicit mandates to achieve specific technical milestones on compressed timelines. The message from Beijing was unambiguous. Find a way, at any cost, on any timeline, that beats the alternative, which is permanent technological dependence on a geopolitical adversary. Then comes the detail that makes the export control strategy look, in retrospect, like it may have accelerated exactly what it was designed to prevent. By cutting China off from EUV, Western governments forced Chinese researchers to explore alternative lithography approaches that the established industry had largely set aside because why develop an alternative when the existing technology works and the market is already built around it? China had no such constraint. It had every incentive to find a fundamentally different approach. And particle beam lithography, a technology that uses focused streams of electrons or ions instead of light, was sitting there, underexplored, underinvested, and carrying capabilities that nobody in the established semiconductor industry had fully pushed to their limits. China pushed them. And what it found on the other side of that research effort is what has the industry worried in a way that export controls, trade restrictions, and diplomatic pressure cannot easily address. Because you cannot export control a scientific principle. And particle beam lithography is built on principles that belong to no single nation. And what those principles actually enable, what particle beam lithography can do that EUV physically cannot, that is where this story becomes genuinely impossible to look away from. The particle beam alternative nobody saw coming. Here is what most people watching the semiconductor war between China and the West have never been told. EUV lithography is not the only way to print patterns onto silicon at the nanoscale. It is simply the way the industry chose the path that got commercialized, that attracted the investment, that became the standard. But there is another approach, one that doesn't use light at all. One that sidesteps every physical limitation, every supply chain dependency, and every export control that makes EUV the chokehold it is. That approach is particle beam lithography. And China just demonstrated it at a level that changed the conversation permanently. The fundamental concept is straightforward in principle, even if the engineering is anything but. Instead of projecting light through a mask onto a photosensitive surface, particle beam lithography fires a focused stream of charged particles, electrons, in electron beam systems, ions in ion beam systems directly onto the silicon substrate. Because these particles carry charge and mass, they can be steered with extraordinary precision using electromagnetic fields, writing patterns onto the chip surface with a level of control that light-based systems physically cannot achieve at the same scale. The critical advantage is this: light diffracts. When you push light-based lithography to its physical limits, the waves of light begin to interfere with each other, blurring the edges of the patterns being printed and setting a hard boundary on how small features can get without heroic and enormously expensive engineering workarounds. Electrons and ions don't diffract the same way. They can, in principle, write features far smaller than anything EUV can currently achieve, not by fighting physics, but by operating on different physics entirely. But this is where the tension in particle beam lithography's history becomes important to understand. The technology isn't new. Electron beam lithography has existed for decades and has been used extensively in research and low-volume chip production. The reason it never replaced optical lithography in high-volume manufacturing is throughput. Writing patterns onto a chip one beam at a time is extraordinarily slow compared to projecting an entire layer simultaneously with light. A single EUV exposure can pattern a chip layer in fractions of a second. A single electron beam writing the same layer sequentially would take hours. At semiconductor production volumes, that gap made electron beam lithography commercially unviable for mass manufacturing, and the industry moved on. Then comes the breakthrough that changes everything. What China's researchers demonstrated is a massively parallel particle beam system, not one beam writing sequentially, but thousands of individually controlled beams operating simultaneously across the chip surface. The throughput problem that made particle beam lithography a research curiosity rather than a production technology didn't get engineered around. It got solved at the architectural level. By parallelizing the beam array, China dramatically collapsed the time required to pattern a chip layer, bringing particle beam lithography into a range where production-scale manufacturing becomes not just theoretically possible, but practically achievable. And unlike EUV, the core components of a particle beam system, the electron sources, the electromagnetic steering arrays, the vacuum chambers do not require a global supply chain of hundreds of specialized Western suppliers to build. China can manufacture the critical components domestically. There is no ASML equivalent sitting at the center of this technology, controlling access subject to export restrictions. The chokehold doesn't exist. And that is precisely what has the industry so deeply unsettled. But understanding what China claimed to achieve and understanding what it actually demonstrated in practice, that's where the real tension in this story begins. What China's breakthrough actually achieved. This is the part where the story requires precision, because in the semiconductor industry, the distance between a laboratory demonstration and a production-ready technology can be measured in decades and hundreds of billions of dollars. Claims matter. But verified, reproducible, scalable results matter infinitely more. So what did China actually demonstrate? And why is the industry taking it seriously rather than dismissing it as state-sponsored propaganda? Chinese researchers, working through institutions including the Chinese Academy of Sciences and several state-backed semiconductor research programs, published findings demonstrating electron beam lithography patterning at feature sizes competitive with advanced EUV nodes in the range of 2 to 3 nanometers using a multi-beam parallel architecture. The key word is parallel. Previous electron beam demonstrations at advanced nodes were achieved with single or limited beam configurations, confirming the physics worked but leaving the throughput problem completely unsolved. China's demonstration addressed throughput directly, showing that a massively parallel beam array could pattern chip features at advanced nodes at speeds that begin to approach the commercial viability threshold. But this is where the industry's concern stops being about the specific numbers and starts being about the trajectory. The semiconductor industry has seen this pattern before. When a fundamental technical barrier gets crossed, when someone demonstrates that a previously theoretical capability is physically achievable, the transition from laboratory proof to production tool tends to accelerate faster than outside observers expect, particularly when the entity driving that development has essentially unlimited capital, a national mandate, and no commercial pressure to protect an existing product line. China is not trying to sell particle beam lithography machines to a global market. It is trying to build enough of them, fast enough, to achieve domestic semiconductor independence. That is a completely different optimization target than the one commercial equipment makers operate under, and it removes most of the friction that typically slows technology transitions in the private sector. Beijing doesn't need particle beam lithography to be profitable. It needs it to work. Those are very different bars, and China has already cleared the first one. Then comes the detail that landed hardest inside the industry. Independent analysts reviewing the published research noted that the multi-beam architecture China demonstrated was not a marginal improvement on existing electron beam approaches. It represented a genuinely novel engineering solution to the parallelization problem, one that Western research institutions had explored but not pursued aggressively, precisely because the commercial incentive to do so was absent, while EUV was working and scaling. China essentially ran a research program that the West had deprioritized, got further than anyone expected, and published enough of the results to make it impossible for the industry to pretend it wasn't happening. And the part nobody is saying loudly enough yet, this is almost certainly not the final state of the technology. What China published is what China chose to publish. The full extent of domestic development, the current state of classified research programs, and the timeline toward production deployment are not in those papers. What is in those papers was enough to worry the industry. What isn't in them may be what changes everything. But a laboratory breakthrough, however significant, only becomes a threat when it scales. And the reason the industry is genuinely frightened isn't just what China built, it's what building it actually means for the global balance of technological power. And those chips would power China's AI systems, its military electronics, its space program, and its next generation of consumer technology, all built on a foundation that the West has no lever to pull. Then comes the strategic dimension that should concern every government watching this unfold. China is not developing particle beam lithography in isolation. It is developing it as part of a broader semiconductor independence strategy that includes domestic photoresist chemistry, domestic chip design software, domestic packaging technology, and domestic equipment manufacturing across every node of the production chain. Particle beam lithography is the keystone, the piece that unlocks the rest, but the rest is already being built around it. If the keystone falls into place, China doesn't just have one piece of an independent semiconductor industry, it has all of them simultaneously. And perhaps most unsettling of all, other nations are watching. If China demonstrates that particle beam lithography can be scaled to production viability, every country currently subject to Western semiconductor export controls has a blueprint for building around them. The technology doesn't stay in China. The knowledge propagates. The export control regime doesn't just lose its grip on China. It loses its grip on the concept of advanced chip manufacturing as a controllable resource entirely. The industry isn't worried because China built something impressive. It is worried because China may have found the exit from a trap that took a decade to construct, and if that exit opens, it cannot be closed again. And what that open exit means for the future of AI, military technology, and global power, that is where this story delivers its final, unavoidable truth. Why this terrifies the industry. Let's be precise about what the fear actually is. The semiconductor industry is not afraid that China's particle beam lithography is perfect. It is not afraid that China will be mass-producing 2-nanometer chips next year. The industry is afraid of something more fundamental and more difficult to counter, that China has identified a credible alternative pathway to advanced chip manufacturing that operates entirely outside the control architecture. West spent the last decade constructing. And once that pathway is proven at scale, the entire strategic logic of semiconductor export controls collapses. Think about what those controls were designed to do. They weren't designed to permanently prevent China from having advanced chips. They were designed to create a dependency to ensure that if China wanted the most advanced semiconductors, it had to either buy them from Western-aligned manufacturers under Western-set conditions, or accept a permanent capability gap that would compound over time. The controls worked by making EUV the only viable path, and then owning that path completely. Remove EUV from the equation, and the entire architecture of technological containment that Washington, Brussels, and Tokyo spent years negotiating and enforcing becomes strategically irrelevant. But this is where it gets darker, because the implications don't stop at export controls becoming obsolete. If China achieves production-scale particle beam lithography capability, it doesn't just gain the ability to manufacture advanced chips domestically. It gains the ability to manufacture them in facilities that require no Western components, no Western software, no Western maintenance contracts, and no Western permission of any kind. The chips coming out of those facilities would be entirely outside the visibility and influence of any foreign government or corporation. The future of computing is being rewritten. Here is the reality that every technology executive, every defense analyst, and every government official tracking this story is now sitting with. The semiconductor industry was built on the assumption that advanced chip manufacturing would remain the exclusive domain of a small number of Western-aligned nations, countries that controlled the equipment, the chemistry, the software, and the knowledge required to operate at the frontier. That assumption shaped 2 decades of geopolitical strategy, billions of dollars in export control enforcement, and every major technology policy decision made by Washington, Brussels, and Tokyo since 2019. China's particle beam lithography breakthrough doesn't just challenge that assumption. It begins to dismantle it at the foundation. Because here is what semiconductor independence actually means in practice. It means China's AI development, already the most aggressively funded artificial intelligence program in human history, is no longer constrained by chip availability. Every restriction, every throttled export, every carefully negotiated ban on advanced NVIDIA processors loses its leverage the moment China can fabricate equivalent or superior chips domestically at scale. The AI race doesn't just tighten, it resets. And it resets on terms where the West no longer controls the starting line. But this is where it stops being an industry story and becomes something that touches every person on the planet. The chips that particle beam lithography would enable China to produce aren't just for smartphones and laptops. They are the processors that run autonomous weapons systems, satellite networks, cyber warfare infrastructure, and the AI models that will increasingly make decisions affecting billions of lives. A China with full domestic semiconductor capability is a China whose technological trajectory cannot be slowed, redirected, or influenced by any external economic pressure. That is not a trade problem. That is a fundamental shift in the global balance of power. Then comes the hardest truth of all. The window to prevent this outcome, if it was ever truly open, is closing faster than the West has been willing to acknowledge. Every month that particle beam lithography moves closer to production scale is a month in which the export control architecture becomes less relevant, the technology gap narrows further, and the strategic options available to competing nations shrink. China didn't win the semiconductor war by beating the West at its own game. It changed the game entirely. It looked at the door the West had locked, turned around, and built a new door out of physics that no government can embargo, no trade agreement can restrict, and no export control list can contain. The future of computing, of artificial intelligence, of military technology, and of global power is being rewritten right now in a laboratory, on a chip smaller than a fingernail, by a beam of electrons that answers to no one.